Hi, everyone. Hope everybody's doing well today. I know some of you, it's starting to get a little stir crazy and things are starting to impact your life. And we'll get through this, as everybody keeps saying. And we're going to finish strong. And that's the only thing we can do. And that's the only thing we can control is our attitude and our effort right now. So here we go. This one's super short. Again, not assigning any homework with this. Just wanted to fill in some stuff. And here we go. So we're going to call this part one. Okay. So stellar evolution, which is what you've watched some um, videos on, and you should be pretty familiar with this topic. So the first thing is this is the Doug Timo original life cycle of the star drawings. For years I kept looking for good life cycle pictures, and I decided to just make my own. So here you go. All stars, and you should have learned this in physical science, okay? All stars start in a nebula, okay? That's like the factory, if you will. They become, and you should have seen that in the video that you watched the other day, but then they become a protostar, and from a protostar, which is a baby star, they enter the main sequence. It's here in the main sequence where they kind of determine what they're going to be. We're going to talk about our sun first here, which is an average mass star, low to average mass, but on the lower end. Our sun is going to become a red giant. Again, that's the expanding of outer layers, which would, when our sun does that, it's going to come over the Earth all the way to Mars, basically vaporizing Earth's atmosphere and everything like that. And that'll be the end of Earth as we know it. From there, it's going to go through what we call a level one supernova. Now, a level one supernova is not the big kind of explosion that everybody thinks of. It's that just shedding of the outer layers. It's kind of like the inner core contracts, and then there's just this massive amount of release of hot matter into the universe. Our sun will be left over as a white dwarf. The white dwarf will just be this nice burning hot ember. It's extremely hot, as you remember from the HR diagram, but extremely dim. And then eventually, like a piece of charcoal, it's just going to burn out, and there's just going to be a piece of charcoal there, and it's called a black dwarf. Okay, so it'll just be this, you won't be able to see it, and it'll just be a large mass there. Now, large mass stars, much larger than our sun, what you've been studying, all starts in a nebula, then to a protostar, then to a main sequence large mass, then it becomes a supergiant. Now, a supergiant, as you've seen in videos and stuff, will become much, much larger. Okay, this supergiant may expand all the way past Mars, almost to Jupiter. Then it will go through a level 2 supernova. This level 2 supernova is the one you see in videos and everything like that, with a giant explosion, release of energy past the plasma state. After that, as you watched in the black hole video, you'll be left over with this neutron star. What I love about that is that if you could scoop up a teaspoon of it, okay, it would be more dense than a cruise ship packed with passengers. So unbelievably dense, almost unfathomably dense for its size. Now, this star would only be about the size of, like, if you took Franklin County off the map and made it into a sphere, which, yeah, it's a big area, but compared to the planet, I mean, we're not even talking about the size of Ohio. We're talking about a small county in Ohio. That's how large it would be, but it's so incredibly dense. And then it becomes a black hole, which you've watched that video on already, and you should be masters of that. What's a low mass star do? Well, again, starts in the nebula, protostar, low mass. And basically what happens is we really don't know, because these low mass stars are not around long enough, and or their light is not around long enough for us to know what really happens to them. So they're kind of a mystery. They kind of burn out, if you will, before we're able to even recognize what they are. So again, I have it all on here as kind of a overall thing. So this one up here would be, yes, that would be a average mass like our sun, large or big mass, becoming a black hole, and then finally a low mass there. And if you want to, you can test yourself. You can pause this right now. You can kind of identify what each one of these are, go back and look. So go ahead and do that if you want right now, and I'll give you a few seconds to come back. Okay, so we're going to move forward. Now, luminosity versus temperature. This all goes back to the Hertzsprung-Russell diagram in the background. Again, luminosity versus temperature. Remember, temperature gets bigger as we move to the left. Notice they kind of put the color spectrum on here. If you remember, the super giants, which were red, were here, and the giants were here, okay? And then we moved to this really blue light because, again, with temperature, again, like we talked about in previous chapters, that corresponds to the wavelength and the frequency, and that produces the amount of visible light that we can see as well. Remember, M is the solar mass, and this would be the standard M naught. That would be our sun, okay? And our sun, and then this would be 1/10 of the size of our sun, and then again, this would be 15 times the mass of our sun. What these are these are ways to track the evolution or where they will eventually end up. Now, I know the arrows point this way, but we start in that main sequence and we kind of go out to these, but these are the paths that we travel. So, for an example, a red giant from the main sequence will travel up here to where those red giants are. A white dwarf, like our sun, might go out to a red giant, kind of fly through this when this is like that level 1 supernova, and then end up down here at a white dwarf. Those huge stars may travel out here to red giant, continue to the supergiant, and then eventually go supernova. They don't end anywhere on here because on the Hertzsprung-Russell diagram, there is no neutron star or black hole, right? That's not, we can't see them, so we can't show them on this chart. So they kind of just end up out here in nowhere instead of going through that level 1 and shooting down here. I can never say this name right. I'm not even going to try. Okay, I can't ever say it right, but this is his limit. Okay, which basically means 1.4 solar masses. The core makes up about 1/3 of the mass of stars. So stars with mass greater than about 4 solar masses will not form white dwarfs. So again, this would be like our sun. Flies around here. Hope you enjoyed that sound effect. Flies around here, and we get down here to white dwarfs. If it was a mass that's 4 or greater, it's not going to do this. We assume that it's going to fly up here and it's going to be large enough that it flies out. And remember, you think only 4 times the size of our sun. Well, there can be almost hundreds of Jupiters that fit just into our sun. So when you talk about grand schemes of how big things are, it's almost unbelievable. Okay. But they will refer to this limit uh, in your problems coming up here. Okay. Now, I can say this one. This is the Oppenheimer-Volkoff limit, okay, of 3 solar masses. The results of gravitational field is so strong that not even light can escape it. Black hole is formed. So with this limit, it's saying basically with their limit, they found that if it's larger than 3, but usually we tend to use that 4 limit before everything else. So basically, I just wanted you to make sure that you've kind of seen these things, kind of understand that this is a Hertzsprung-Russell diagram in a way and how we read that. Okay? So again, super easy week this week. Just tend to focus on these notes, and remember to also just focus on doing our fun little assignment that was done for the week. Other than that, if you have questions, this is a great week to make things up if you don't have them done yet. And again, I hope other classes aren't trying to crush you. That is not my intention. Have a great day. We'll talk to you later. Teamatron out.